let's do a few more examples. Let's do an easy one just to kind of warm up. So let's show that 8b is true, and a reminder what 8b is from the previous video is that A union the empty set is indeed A. So pause the video now, try this yourselves. It shouldn't be too long. Remember that the empty set has nothing in it. That's going to be entirely key to this. Okay. So let's start. Let's do that. Let's say proof first. Proof. Let's first show that A union the empty set is a subset of A. This is, in some sense, a very easy proof because the empty set's kind of doing nothing here. We just have to make sure we're using the definitions properly. Okay, so let's let X be an element of A union the empty set. And we need to show that it's in A. That's pretty easy. Well, this means thus X is either in A or X is in the empty set. But can X be an element of the empty set? Of course it can't. But since the empty set has no elements, that's the definition of the empty set, we know that X can't be an element of the empty set. Nothing can. So that means that X must be an element of A. So we have that X union the empty set is indeed a subset of A. I took an element from the left-hand side and showed it was in the right-hand side. Let's do it the other way around. Let's show that A is a subset of A union the empty set. This one is very easy. So let A be an element, or X be an element of A. And just like from the previous video, since X is in A, X is going to be in A union whatever. So thus, X is in A union the empty set, since it's true that X is in A or X is in the empty set. This bit makes no difference, right? Because it's in A. We know that the statement X is in A or X is in the empty set is true because one of the parts is true, because this is an OR. That's all we need. So what does that mean? Thus, we're done. So putting these together, we have that A union the empty set equals A. And just to be more explicit, so over here we showed that A union the empty set is a subset of A, and over here we showed that A was a subset of A union the empty set. So that one wasn't too bad at all. Let's prove a couple of those results involving subsets themselves. So let's scroll down. Let's do 12a here. Let me remind you what 12a is. First, it says that A is a subset of B if and only if the complement of B is a subset of the complement of A. These are logically equivalent statements. They're both. So it's going to be impossible that one is true and the other is false. They're either both true or both false. Okay. So let's go ahead. Remember we have two arguments to do here with an if and only if. So let's prove this. So let's do the if direction first. So we're going to prove that if A is a subset of B, then the complement of B is a subset of the complement of A. So that's what we're going to show. All right. So let's assume that A is a subset of B. We know that what that means. That means any element of A is also an element of B. Okay. So we need to show that the negation of B is a subset of the negation of A. So we'll take an element from the negation of B, and we need to show that it's in the negation of A. So to show, oh, wrong color. Got a color switch there, sorry. To show that the complement of B is a subset of the complement of A, and the tool we have to work with, the assumption, is that A is a subset of B. Okay, so let's go ahead. So let's pick an element in the complement of B. So this means that X isn't an element of B. Well, if X isn't in B, that means that it can't be part of any subset of B. Since X isn't in B, then, maybe I'll write it like that, then X can't be an element of S for any S that's a subset of B. Remember, subsets are made up of elements of the set, so if it's not in the set at all, it can't be in any subset. So if it's not in that, by our assumption, we know that A is a subset of B, and thus we've shown that X can't be in A. So that's the first direction. If X, or I should say, let me finish this. If X can't be in A, thus X is in the complement of A, and we have that the complement of B is a subset of the complement of A, since we started with an element in the complement of B and showed it was in the complement of A. Now let's do the other direction. Let's do the only F bit. So now we're going to assume if the complement of B is a subset of the complement of A, then A is a subset of B. And it's going to be a very similar proof. So we're going to assume that the complement of B is a subset of the complement of A, and we want to show that if an element is in A, it's also in B. So let's pick an element from A, and we need to show it's in B. So let X be an element of A, and the assumption that we're using is the complement of B is a subset of the complement of A. So this proof basically follows the exact same steps as the first direction, the if direction. So let's just write it down. So We're picking an element in the left-hand set here. Now, what does that mean? Well, it means X isn't in the complement. And if X isn't in the complement, then we can use that same subset argument. Since X isn't in the complement of A, then X can't be a member of any subset of A. For any subset of the complement of A. And by assumption, we know that the complement of B is a subset of the complement of A. So X isn't an element of the complement of B. So it does mean that it's an element of B itself. If it's not in the complement, it's in the set itself. Well, what do we have? Thus, we have that A is indeed a subset of B, since we started with X being in A, and using our assumption, which we used here, we showed that it was indeed in B as well. So A is a subset of B. So now the result is indeed proved. I'll leave 12C as a little bit of an exercise for you guys, but hopefully these two examples kind of give you a flavor of how to do proofs with sets. We'll explore a little more using these set equivalences in the next video so we can simplify just like we did with logical equivalences.